Hello guys. So I've been working on this some idea. So I have an idea. So I was working around building a project around it. So I guess most of you are aware of this generative AI growth and uh, all the popular models, Llama, Gemini. Then you have Claude, OpenAI, and all those fights between LLM, between companies. Yeah. So I was reading about them, and uh, one very key uh, concept that catch my eye was this knowledge graph. Uh, so yeah, this is how a knowledge graph looks like. So yeah, and before we, so for the audience who don't know, like what's the context of it, so right now we have LLMs, right? Uh, Large language models. Yeah. So these are essentially like if you guys are familiar with NLP domain of deep learning. So there are various algorithms were made in the past so that they can generate text as human beings. So and by generation mean like there are many tasks in NLP like something like sentiment uh, analysis. Then you have NER like name entity recognition, and predominantly you have this generation of texts. Okay, so yeah, so this is where all this LLM blooming is happening. So these large language models are capable of generating text, and it looks very like similar to how a human being would have like written those texts. But nowadays there is a very popular concept like RAG is happening, and many services and software softwares are building around this concept. So this is something we call it like retrieval augmented generation. Now it's nothing fancy here. So if you guys are if you guys have ever given a reading comprehension kind of exam in your English test, so you must be familiar with this kind of question like uh, reading comprehension questions. Let's look at an image. Yeah, it's something like this. Let's open the image in a new tab. It's quite small, but I can make it large. So yeah, so generally what happens is, so let's say you have a user and you ask a query, and by query it means like not just like a question. It can be anything. Okay, okay. Any input text you are giving, we generally term it as query. Okay. Now, when you ask it to directly LLM, then LLM will generate a output response. So it's basically some reply to your query. Okay. But the issue is, so LLMs are trained over a large and massive data set, which are like uh, in different domains. So there is like medical domain, uh, like physics, maths, and even economics, uh, literature, many domains they are like trained. But the cool thing about LLM is like with respect to the context of the question, like within the question, was like in what domain it should lie. So they are doing a pretty good job in like generating a proper response. Okay, but sometimes they even fail to capture the proper context of the question, and this is where this kind of concept comes into play. And that basically what it does is, so uh, given your query to the LLM, you can also pass some context to the LLM. Okay, now this basically means something like this. So for example, if I want to ask a question like who is going for a walk, if I randomly give it to a LLM, it will like it can generate any response, right? Because this question is pretty generic. But if I provide this context here, okay, like Vis is going for a long walk, then LLM will try to reason with respect to the question and the context, like which line better align with this question. So it will answer Vis. Okay. Uh, so yeah, that's the concept. Now, so yeah, within this query, we will provide the context also, so that the LLM will have an idea like with respect to what that like we are asking. Okay. Uh, so that's the concept of RAG, like retrieval augmented generation. So generation LLM is doing fine, but we want to augment it, like help it by doing some retrieval on the documents that we have. Okay. Now documents is a generic term we use in RAG. Now this document can be a book or a PDF. Even images are also possible, like multimodal LLMs. And yeah, so books. So this will fall in text category. So wherever you are finding text, you can build a pipeline so that from the documents you can extract out the text. Okay, let's say text extractor pipeline, and from that you can ask any questions from this blob of text. Okay, and then yeah, you can ask directly ask the question to the LLM. So the LLM will figure out, okay, user has given me this context and this question, so how should I answer it? Yeah. uh so on this, multiple technologies are involved. So the most simplistic one was like this embedding approach. uh yeah, let's zoom it. So this RAG system, okay. So generally technologies are building upon this services, okay, or I can more precisely it's like retrieval services. Now there are certain algorithms involved in this retrieval. So yeah, like I said, the popular and the most basic one is the embedding approach. Okay. Then there is involvement of knowledge graph, which I will be talking about. Okay. And then there are like feature stores. Yeah. Now, if you guys have an idea of like how things work in NLP, and or like how things works in neural network, so you must be familiar with embedding. So embedding is something like a vector representation of a thing, you can say. So generally what happen is, so let's say you have a neural network, something like this. Okay, and it is connected to some neurons. Let's say I have more this, and let's say this is like fully connected. All the neurons are connected to each other. Okay, I will not be drawing it everyone, but yeah, you get the idea. And let's say they are producing a output something. Okay, uh, let's call it. And then now what embedding means is, let's say if I pass in some input, okay, this can be image or a text. Okay. So how the neural network will perceive here is, it will try to find a representation of this image. Okay. And this representation will hold only the useful information on which we will be doing some prediction. So for example, if I say, let's say we have a cat picture. Okay. Phew, I don't need you. Let's say I have a cat picture. Okay. I'll be drawing some required features for the cat. Okay. Let's say this is a fat cat. And see that's sitting there waiting for food. Let's say this is a cat picture. Okay, I'm just drawing with my mouse, so yeah, feel free to comment how the cat looks. So yeah, if I'm drawing this cat picture now, let's say when you are a kid, when did you know like this thing is called as a cat? So someone must have told you, like, whenever you are seeing features like, hey, there is a tail here, there are whiskers here, and the ears are like this, and even the size of the cat. Okay, all these features. So based upon these features, we classify this image or this animal as a cat, right? So yeah, similar to that only we teach, uh, like our neural network that thing. So basically we give this text. Okay, now there are certain algorithms involved in the training process. Okay, so what this algorithm does is, like, based upon this input, okay, we will try to tell the neural network, hey, you should predict this as cat. Okay, so it's something like, we are doing a function mapping kind of thing. Okay, if we give x, you should result y. Okay, so some f of x is happening due to which y is, due to which given a x, y is happening, and this function is something we are trying to approximate with neural network. Okay, why neural network? Because like we have many algorithms for approximation, like Taylor series, we have, then even Fourier series, we have. But yeah, those things doesn't work well with complex data set, because they have multiple assumptions. And yeah, neural network is something we can control on the parameters, because whenever we are approximating, we actually don't know the underlying number of parameters we will be needing it. And also computation of Taylor series and Fourier series kind of complex, like they will take much more resources. So yeah, so scientists just like Jeffrey Hinton, even Andrew is a teacher, but yeah, so so like people like that, so they build out this concept. I'm not saying Jeffrey Hinton himself like build out neural network, but it was there. So because of neural network, yeah, uh, finding this kind of, like, approximating this kind of complex functions were much more efficient. So yeah, this was all about neural network. So let's come back to embedding. So what neural network does is, so if you look at this layer, let's choose green. Okay, so if you look at this layer, okay, we call it layer, and all this, the circles, we call it neuron. So just like our brain, we are trying to create some neurons. Okay, they have some activation functions. Okay, and when we are connecting multiple neurons, they are able to approximate complex functions. Okay, now if you see this layer, if I pass in an image, okay, so it will give me some, if I only take the output of this, okay, so it will look something like, let's say 0.1, 0.2, 0.99, something like this. We have 4 values, yeah, will look something like this in a matrix form, okay. And this matrix form is something we often termed as vectors, okay. Now this vector, you can say, can help us as a embedding, and embedding. I will not go very deep, like how exactly deep neural network works, but yeah, the idea is something like this. So each layer of neurons uh, computes a vector, okay, and then that vector is passed on to next layer, like output of where is this, output of this is passed on to this, then they will also compute a vector, then output of this will be passed on to this. Now here some other activation functions we will be having, which will use this vector and compute a single value, okay. It's like based on a problem statement, like let's say if our problem statement is like given an image, classify whether that image holds a cat or not, then it's kind of a single value problem, right? Because we just have to predict the probability of cat or p of cat in the picture, okay. Yeah, so we will have the activation function which will use the output of the penultimate layer, and then it will compute the probability. So yeah, you guys can like read about it. So the idea behind is like whenever these neural networks are trained, so they are trained in iterations. Like one iteration, the whole image will go, like whole sets of image will go. Some weight matrices will change here. Okay. Okay, based upon the number of neurons, and this weight matrices look something like this. Something like this, but these are the like the outputs, like all the RGB values here in the image, okay. So all those will be multiplied with the weight matrices, then this kind of output form will look here, okay. And this weight matrices that we have, okay, so this will be something we can term it as multipliers. Let's like to be very simple, okay, multipliers. And whenever we are sending image, okay, so all the RGB values in the image, okay, all the pixel values in the image will be multiplied with this to generate this kind of result, okay. Now this result we call it as a embedding, okay. Now how does this embedding help it, like whenever we are training them, so yeah, like I said, they are trained in multiple iteration, so this neurons will learn the representation or the underlying representation that are there in the image, and these representation will help us in predicting whether cat is there or not. Now this representation will mostly like, hey, whether there is a whisker, or hey, what's the color of the cat, okay, hey, is there a tail, or are there whiskers, so something like this will happen. So we exactly don't know like what all things it is learning. It's in it, like it is still a black box, we don't know, but we always assume that uh like this kind of things it is trying to capture, okay. Now we can pull out one of the outputs of this neuron, like of this layer, and we can use them as embedding, okay. Now this is the image example. Now if you think of a text, okay, if you have text, a blob of text here, okay, let's say you are training a neural network for let's say sentiment classification, okay. or let's say sentiment analysis, whether the sentiment of the sentence is good, bad, or like anger is there, or oh, that's kind of emotion, but sentiment is mostly like positive, neutral, negative, something like this. You're kind of training. Okay, now you will again have a set of neurons like here. Okay, and these neurons will again output your vector. Okay, now this you can use as embedding. Now what all things this embedding will provide is like, first of all, this embedding you can control the size of the embedding. Okay, and there are certain algorithms from which uh, you can like, so yeah, from this embedding itself we can also call it as, we can encode the text into a vector representation. Representation, yeah. Encode a text into a vector representation. So this embedding, sometimes people also call it encoder. Okay, because we are kind of encoding, like similar to kind of encryption, but not exactly encryption. It's some kind of like changing the paradigm of your input to some other paradigm. That's why we call it encoder. So yeah, encoding this text into a vector representation, and we have the control on the size of the vector representation, because whenever we will be building this neural network, we will be giving the number of neurons we want, right? Yeah, and based on that we can control the size of the vector representation. Now how this will help is like, think of a DB you are building. Okay, now when you will be like storing text, okay, or strings. Now we know in like in C++ or in C, like our first computer class, so whenever we were taught about data type sizes. Okay, now something like this, data type sizes. Do I have something? Yeah, you can see here. Let's look at C++. You can see like a character takes around 1 byte. Okay, and in a string we kind of store a array of characters, right? So it's like you are consuming 1 byte per character that you have, even if it is a space or a small full stop in your sentence, you are kind of consuming that. And let's say you have a 1,000 character sentence. Okay, now this will take around 1,000 bytes, right? But we can encode the same sentence using a neural net. Okay, and reduce its size to the embedding layer that we are choose. Let's say there are around 500 neurons here, let's assume. Okay, now instead of storing this sentence in my DB, I can store this 500 dimension vector in my DB. Okay, now yeah, so this will be like somewhere like, so floats are taking like 4 bytes, and usually this embedding underlying like data types here are float. Okay, but yeah, I hope you get the point. Like, so it will like obviously increase here, because if you're storing 500 values here times 4. Okay, so this is like more than this, but let's say instead of 500, let's choose like 100 neurons I have here. Okay, now if I have 100 neurons, so instead of 500, 400 times, like 100 times 4, that would be like 400 bytes I will be storing per sentence, which is like much more reduction than this 1,000 bytes that I was consuming by storing the original text as it is, right? So yeah, in this kind of concept, like embedding helps us. Now another most useful case of embedding is like, so it's something like with this new, like from this neural network, you have some kind of a vector representation, right? Some n-dimensional space you have. Okay, yeah, multiple dimension, like all of them are orthogonal, I'm saying. So because that's how we present dimensions, right? Now you have some n-dimension space here. Okay, and in that dimension you have a representative vector for a thing. Okay, so let's say it will look something like this. Let's say v1, or let's call it, let's say vcat. Okay, now interesting thing is, like, when I will be having a embedding for a tiger image. Okay, so tiger image will look something like this, let's say. Okay, and if I have a fish image, fish will look something like this. Okay, now the key idea is similar things will have uh, you can say similar vector representation. Similar things will have similar vector representation. Now how this will help is, like, think about a clustering kind of task. So if I want to group all the like, let's say cat family, let's say I have a bunch of vectors of animals. Okay, let's say I have crocodile here, let's say I have a snake here, v of snake, and let's say something like this is there. Okay, now if we visualize this vector embeddings in this n-dimensional space, what will happen is, like, cat and tiger will have a more similar vector representation when compared to cat and a snake. Okay, I'm just drawing out the arc. So let's say theta 1, let's say theta 2. So theta, let's say cat to tiger, will be lesser than theta of cat to snake. Okay, now how this will help us, like, yeah, like I said, like, this will help us to group things, or let's say presenting clustering. So, or we can extend this idea to something like predicting outliers in a data. So if I draw out all the distribution of my data and some of the points are, like, not aligning with all the maximum number of points, something like that, then I can, like, easily predict whether that's a outlier in my data set or something. So yeah, now, so yeah, this is how embeddings are used. Now if I go back to our RAG concept. Okay, now embedding will help us is, like, so if I build a document. Okay, let's say I took Harry Potter book. Okay, now people who are, like, familiar with Harry Potter, all the parts, uh not movies, not movies. Okay, books. Okay, then you guys must be aware of this character, uh Regulus Black. I don't know whether I'm, like, writing his name correctly, but this character was not shown in the movie. Okay, only name has arrived when, I guess, Dobby or some elf in Sirius Black apartment, just like, he was a servant to Regulus Black, and he had the key um to the, I don't recall, but yeah, something like that. Like, the elf knows about the Regulus Black, and that was the first time in the movie when Regulus Black name was coined in the movie, and Harry Potter, like, Harry Potter got to know about. But in the books, we have a proper description about Regulus Black, and how was in the Black family and what sacrifices he made in order to, like, defeat Voldemort. Okay, something like this. So let's say I take Harry Potter. book, okay, and I extract out all the pages, okay. By extracting out, like, I'm not saying like tearing all the pages. Think of in a coding aspect. So extracting means like you are writing a code that can read this, let's say, PDF, okay, and from that PDF you can collect a list of strings, okay, and these strings are basically one pages from each book, okay. Now if I do this, and now for each text that I have, text or string, okay, I build out a vector representation, okay. Let's say v page 1, v page 2, v page 3, something like v page, and something like this, okay. Now let's say I have a service that stores all this, okay. Now it also provides another feature, like this is one feature, like all of the vector representation of the pages are there. Now the second feature is like I can give out a query to this service, okay, and it will find me only those pages which are relevant to the query, okay. So let's say v of page I, uh, such that, let's say, similarity, or let's say relevancy, relevancy of query with my v of page of I is like greater than or equal to certain threshold, okay. Let's say this threshold is somewhere 0.9, 90%, okay. If I have this kind of a service, okay, then I can improve my RAG service, like simply asking a query directly to the LLM. I have this query. Instead of asking directly to the LLM, I can first give this. So instead of doing this kind of naively, what I can do this first, I will make this query and hit this service, okay, and extract out the pages, okay, so that the LLM will have a idea, okay. So let's say the LLM is trained on movies subtitles, okay, then it will not have a good context about Regulus Black. So if I ask a query to the LLM, like say 5 lines about Regulus Black, so it will, so like its domain is like uh, enticed to the whatever is there in the movie. But if I give the books, okay, and I extract out the relevant pages that I have, okay, then I can pass those pages inside a prompt, okay. This prompt is nothing, it's simply a text, okay. Inside this prompt, so let's say I have a prompt structure like this, where I am putting all the pages content here, and then I'm asking the query here, and then if I ask the LLM, then LLM will have a better idea about Regulus Black. Let's say 2-3 pages were only dedicated for introducing Regulus Black in the book. Now LLM has all those data. Now he can reason out and find all the chunks which are related to Regulus Black. So yeah, so this is how embedding approach is used in retrieval service. So yeah, sorry, someone was at my door. So yeah, this is how embedding approach is used. Now, this relevancy you can think of like simply computing the cosine similarity between our query and the page. So this is something this. So this is embedding approach is pretty quick, but there are some downsides of this, because when you are doing this embedding, so it might happen like in your page, or let's say this is how your like that blob looks like the text. Okay, now there are certain lines which mention Regulus black here. Okay, but rest of the other lines are like jargons which are not relevant to the Regulus black. Okay, say not relevant. Okay, and these things are relevant. Okay, now your pages will look like this. Okay, now when you will be like giving it to the LLM, like this whole page, sometimes it might happen the LLM can take out this non-relevant context and will give you some jargons in the response. Like it will be better than what you will get like directly asking the LLM, but it will not be something which you like which will satisfy you. So what researchers have done that like, so for every text chunk that you're looking at, what we can do is like instead of giving out the entire page, we can divide them into text chunks. Okay, so let's say I will take this part, then the next part I will take from this to this, then the next part I will take from this to, let's say, this up to this, so something like this. So there will be some overlaps between the text chunk, so I can visualize it more like, let's say Ravi is the eldest son of Hari, of, let's say, Harry. Okay, uh so how you can like divide them into text chunk is like, let's say this is the entire content in your page, so you can take a text chunk like this, next thing can be this, then next one will be something like this, then next one like this, like this. You can take this and instead of storing pages, you can store this text chunk and extract text chunk embedding instead of vectorizing the pages. Okay, now this is much efficient because pages can have a lot of data, and having a neural network to vectorize pages will be computationally expensive because all these pages we have to represent in some form. Okay, now that form will again be a set of matrices, and then that set of matrices will be given to the neural network to compute the vector representation. Now storing all this large data will like increase the computational cost. Now if you are rich, then you don't really care, but in order to do it efficiently and in order to give this idea to general people, so people uh, tried vectorizing this text chunk, like first getting all the pages, then from the pages extracting the text chunk, and then running the vectorizer on this text chunk. Now this service will hold the text chunk embedding instead of page embeddings. Okay, now this will show a little improvement because here this will be rejected and this will be oftentimes will be accepted. But yeah, here also this text chunk size, okay, this is something will vary from document to document. Okay, now this is kind of, we call it as a hyperparameter. Now we don't know the definite size. We will be like, mostly this process is kind of done using hard coding, and somewhere like people often use some kind of a stop word kind of mechanism, and they have certain algorithm that will predict, hey, at this sentence like nothing is related after this. So because in paragraphs what you have, like you have a text here, you have a text here, you have a text here, and after this some new text come, so these two are related to this, but this new text will not be related to this. Okay, then you know like, hey, I can put all this text chunk here. Okay, but even with this approach, this is not efficient because question to question it may vary, like, hey, like for one of the question, these two are relevant, this is kind of unnecessary, but you just put them because these two are related, something like that can happen. Okay, so that's why vector embedding approach is kind of very naive. It's not naive, like it's good at some cases, but often they fail to capture the relevant context with respect to the query. So another popular idea that we have is having a knowledge graph kind of thing. Now, knowledge graph is different from a vector approach. Okay, now it is something very close to uh, how we find things. Okay, so here the idea is, so you will have some representation for the text chunk, and we term them as nodes. Okay, now the connection between each node will be the relevancy or like the similarity of these nodes to each other. Something like this. It's a fully connected graph. I need a connection like this. Okay, now here edges will be representing a mathematical quantity that can tell how much these two are related. Okay, sim or say similarity of node I to some node j. Okay, let's write it properly. So yeah, you have this kind of fully connected graph, and node will be representing some information. Okay, so they can be text chunk, or let's say a representative word. So for example, let's consider Regulus flag itself. Okay, some kind of a entity. Okay, entity. Okay, so some kind of entity you can think these nodes are. Now these entities have some similarity in between them, which are represented in edges. Now the idea of knowledge graph is like, so in vector representation, what we were doing is like, given a query, we were using this service to find out the relevant text chunks, right? Now in knowledge graph, what we do is, given a query, okay, we pass it to here. Now in this query, whichever nodes are like mostly related to the query, let's say this one and this one are like highly related to the query. Okay, now we can directly extract this, but we can do a DFS kind of a thing. Okay, so that we can capture more information for the query, like with respect to the query. Okay, so the node traversal happens something like this. So like the, like if my source node is this, let's say source 2, source 3, something like this. Okay, so let's say if I do source 1, okay, what's the probability of going to this node? Okay, like all this are selected, right? What's the probability of going of selecting this node, okay, of selecting node I, given that source is selected and this query is asked? Okay, so this will be like a chained probability. Okay, now let's say I'm at here, let's say this was selected. Okay, now from this node, where should I go? Okay, then we will be selecting a node which will maximize this probability. So let's say node J, given that source 1, this query is asked, and node I is selected. Okay, so our traversal happen something like this, or happen in the direction where this probability is max. Cool. Now this is something very intuitive. So think of something like let's say let's talk about algorithms. Okay. Now if I draw out, like let's say I have binary search here. Okay, I have a node like this. Then I have let's say DFS here. Okay, and then let's say I have divide and conquer. Okay, and other popular algorithm, let's say Euler path, something like this we have. Okay, okay, so all will have some certain similarity in between them. Now if I ask a query like, hey, I have a sorted list. Okay, sorted list given, find the uh, how can I find an element X? Let's say for some reason this was selected, divide and conquer. Okay, now from this divide and conquer we can do the traversal, this probabilistic traversal, and we can land upon our binary search kind of algorithm. Okay, so we can build out this traversal, and once we have the set of nodes for which this is max, okay, we can collect all those entities, let's say, or nodes. Say set of nodes, uh, entities, we are calling to set of nodes. Node I is for I we selected. Okay, something like this. Okay, I may not be writing the proper notion, but something like this. We have entities, then we can use the information in this nodes and generate our context. Okay, and yeah, similar to our embedding approach, we can pass it to the LLM, this context plus query, this prompt template to LLM, to help the LLM to better reason this. Okay, now this is very interesting idea, because very often what people are doing is like, so let's consider you take this LangChain or this Llama-index kind of this open source project. What they do is, so they don't use this kind of approach. Okay, so their general idea is, so they I don't know, like, but people are still using it, but their approach is like, hey, I will divide the I will get the document. Okay, from that I will be segregating into pages. Okay, and from each page I will be developing some text chunk. Now from this text chunk I will be generating some triplets. Okay, now these triplets are something in the form of subject, uh, predicate, uh, subject, then relation being the edge, and predicate. Okay, now they do something like this because so these are like frameworks where they are built upon some paper, but their idea, I don't know, like it's just like hard to digest for me. So what they do is like from document to page to text chunk to triplets. Okay, they extract out this. Now wherever this subject is present in a text chunk, they will simply store it. It's like some table you can consider. You have some keyword here, and you have a list of text chunk where that keyword has appeared. Okay, in a table. Okay, key and the list of text chunk where this key is there. So for example, like let's say the king of Westeros is bad, something like this. Okay, now I can extract I can create a triplet, something like this, like king uh, bad Westeros. So this will be an example triplet, and what I will be storing in this kind of a table is like, hey, like this entire sentence for this king, and similarly for this entire Westeros, this sentence. Okay, now this doesn't make much sense because when you are using this kind of triplet, because these words are kind of fine, but sometimes uh, their coding also uses this kind of word like the, of, because of which these entities are associated to very large number of text chunks, and from that they perform a DFS kind of a thing, and there is no probabilistic uh, threshold, like there is no probabilistic traversal happening. So whatever uh, entities are selected, or let's say triplets are selected, and from there they're like traversing and collecting all the text chunks, and from that they are building out the context, and this context is pretty huge. Okay, and this selection of triplet is happening like given a query, they have a pipeline which again extract out triplets from the query. Okay, now this triplet and whatever triplets we have in our knowledge graph, okay, they do a vector similarity. Okay, some similarity score they compute. Now once let's say this um, is selected, so let's draw it out properly. So from this query we will be extracting some triplets. So let's say triplet of query 1, or let's say I will have a bunch of triplets. Okay, and in my service I have triplets. Okay, let's say DB, we call, let's say KG. Okay. Here I have KGI. Now they compute the similarity of this two. Okay, now this similarity is like cosine similarity, and they threshold it with a value, and from that they have the like the whatever triplets are similar to this triplet, and from that in this triplet whatever subject, um, rel and predicate we have, we just pick out some top k sentences from this object and object of triplet KGI. Okay, and they build out a context. Now this is not much sense, right? Because this looks more cool, because we are starting with some source nodes, then from that we are doing a probabilistic traversal to get out like to get the next set of nodes. This is kind of intuitive more, right? You guys can like ping in the chat like whether this idea looks cool, or the idea that this LangChain and Llama-index are building in the knowledge graph, that is more efficient. So yeah, I was planning on building a project based on this idea. Okay, and I will be reading a lot of papers and articles, and it's something in my mind I always wanted to do. Like the first time I used Llama-index and I went through the code, I was like, oh, holy fuck, what the fuck is happening? So initially, for some of the questions, their traversal approach was giving some good context, but as I go deeper into, so I was also working on a project in which I was using Llama-index, but as my question went more complex, the relevancy of the context was not that. Okay, so I stopped using Llama-index. I went to some other approach of doing that, but in that uh, crisp, like I had this idea, hey, I can do better than this, I can code out this. Okay, so yeah, so I was thinking of building a project around this. Now, for generative AI, those who are not familiar, like those who don't know, like uh, mm, Gemini is free for public, but there are still some nuances which you guys should look. Like the rate limit is pretty low. Okay, so like 15 requests you can make with Gemini 1.5 Flash something. Okay, uh, so yeah, I was thinking of building this project. I'll be doing this coding in Python. Okay, so yeah, so you guys can like ping in the chat whether you think it's a good project, or what's your reaction on this project. This is something I'm doing for myself, but I will be uploading some videos on it, so that beginners who are like new to this Python and machine learning field, they will have an idea like how to code, and how to structureize their project. I guess most of the times, like you can directly ask GPT and get the answers, like how to structureize the project or how to do a task. But if you guys are like interested in um, Pythonic project building, so yeah, you can watch my this. I will be uploading this video in a playlist, so you can follow that playlist. And yeah, I'm not claiming that I know all of like project structuring, but I think I have a good idea based upon my experience. So yeah, so yeah, I have to go somewhere now. So I'll be ending this video. But yeah, I will start my project, and I was thinking of doing some live sessions also. So yeah, you guys can like feel free like what you feel about this project, and if you think like this idea is not that good, or some inefficiency is there in this idea, then just ping in the chat. So yeah, I'm open to all the comments that you guys giving. So yeah, just stay tuned to watch more videos, and yeah, I hope you guys learn something new. Although my intention was not to like give any knowledge to you, just like about the project that I will be building it. But if you guys think like I have tell like something you didn't know, so if you learn something new in that aspect, then yeah, you can like the video if you want. So cool. Stay tuned to watch more videos. Adios.